The line integral is used to calculate work in physics. So if you're not familiar with line integrals, this is a little introduction in how we define a line integral and how we use it. So work, as we've seen in let's say physics 1, we'll start with that. You might be more advanced in it and you can kind of skip this part of it. But we define work as a force applied dotted with some infinitesimal displacement, or the differential of dx. So what we had is, let's say we had a horizontal surface, we have a box. In physics we like our boxes, we like our spheres, and we are moving this box to some new location, a new position, and this distance here is what we call dx. So this is infinitesimal displacement dx, and we have a force that applied to this box. I use a different color here, and let's say we just applying some force in some direction. Okay. And the question would be, what is the work done in moving this box, this distance, this displacement, due to this force? So that would be this integral right here. And if you're in physics 1, we do not really know how to deal with integrating vectors. So instead, we write the dot product as the magnitude of the force times cosine of the angle, and we'll get into what that angle is, times the magnitude of that infinitesimal displacement, where the angle is the angle between the displacement. So we could even put a vector onto this one here as well. So a displacement vector, the x vector, and the force vector F. So the angle between those is what we use in the dot product. And then if we know the magnitude of the force, which we often did in physics 1, we know the angle. There would be two constants. We could put them outside the integration. And we're integrating over the displacement. Let's say we're going from some position x1 to some new position x2. So our limits of integration x1 and x2. So that simply becomes the force times cosine theta times whatever displacement we may have. So that is the work we're seeing in physics 1. And this is an example actually of a line integral, but it's a one-dimensional line, and it's a horizontal line, or it could be a vertical line depending on the orientation of the object we're moving. But it was always a straight line. What happened if it was not a straight line? So in principle we could say, here's a point A, here's a point B, and we take an object and we move it along some path in direction from A to B. What is the work done? Well, we could imagine, say, well, if we could take this part here, this is a straight line segment, right? We could in principle say, at this point here we have some force F. At the same time we're moving some small distance here, some infinitesimal distance. That is our dx. And so we take this line segment and we break into a bunch of tiny little straight segments, and we add them together. That will give us a total work, and that's exactly what we do. So we write that as the work is equal to the integral of F along, I should not write x here, instead of x, you can erase this here without erasing all of it. This is dl. It's a small line segment. So it's the force dotted with that dl segment. And that's integrating from point A to point B. Or we could write it as, sometimes we may write it as just along the curve L, where L is simply this curve or line, hence the name line integral. Okay, so that's a different notation. There's even one other notation to indicate that this is along a curve or along a path or along a line, and we may see some sort of a symbol on it, like looks like a half circle, just indicating that this is along some curve or some line. So different notations for the same thing. So this is great. Again, we may not exactly know how to integrate with vectors, so we have to find out to convert this into something we know. So let's say, okay, let's do the same thing as over here. The work done. We take the dot product, so that's the magnitude of the force, cosine of the angle, and dl. And this is from point A to point B. Great. What about the force? Well, we have to look at each element. Is the force constant? Well, it may or may not be. In physics 1, we were so used to just dealing with constant forces, we just pull them out outside integration. It was easy. In physics 2, classical mechanics, forces are usually not constant, so we cannot pull that out. So we need to keep that inside the integration. What about the angle? Well, look at this up here. We make a little sketch here. Here's this little line segment. Gonna extend the line over here. Say, okay, here's the angle theta. But we can see that as we move along this curve, if this force maintains the same direction everywhere, then this angle is going to change. So the angle is not constant either. Well, it makes this integral a lot more complicated. Not only do we need to specify how the force is varying, if it's varying, but the angle is very likely to vary as well. And that makes it more complicated. So this version is not that useful to us. It may be useful in a few applications, but in general it is not. So instead, we're going to write it in a different way. Remember, the dot product can be evaluated in two ways. We can use the geometric form, where we use magnitudes and angles, or we can use component form. The component form of the dot product, so we're going to say that the vector force is an x component times this unit vector in the x direction. Same thing for y. And the same thing for c. So this is a three-dimensional configuration. Our dl vector, that little displacement vector we have, will also have components. We can call them dlx in the y direction and dly in the y direction and dlc in the c direction. When we take the dot product between these two vectors, it's the summation of the individual components multiplied together. So we can write this integral as x component of the force times the x component of the displacement, and then we sum them up. DLC. Okay. And now we have an integral of three terms. So in principle, we could take these here and we could write this out as three integrals. 1 over x plus 1 over y plus 1 over c. Okay. So this notation using L may still be a little bit iffy. So if you look at the L vector over here, that dl vector, I'm going to draw it right here. Just enlarge it up a little bit. This is its x component right here. This is the y component. But the L component is just a projection onto the x. So that's actually our dx, whereas the y component is dy. If I take this as the plane of the xy reference frame, which means that dlx is just the equivalent of dx. So let's write that slightly different now. Integral of f of x dx plus f of y dy plus f of c dc. Okay, so that is the work done. I'm going to frame this one here, and then let's look at it. So what we have here is the x components times dx. So if we know the x component of a force, we have Ex. This is just a one-dimensional integral that we learned in Calc 1. And it's something we should be able to integrate with ease, at least in most cases. So what we have taken, we are taking our dot product, where we're dealing with vectors, the integration of that line integral, and we convert it into 3 separate integrals, one for each dimension in our Cartesian coordinate system, x, y, and z. So we're going to use this to calculate the work when we work in 2 dimensions. And we'll do that as an example in the next video.